at the end of class last time, we took a look at the system performance equation. And we saw that the total time that it takes a program to run is the product of 3 terms. First being the number of instructions per program that has to execute to complete the computation. And the second one, the number of cycles it takes each one of those instructions to execute. And the third is the time it takes for the cycle. And what we said at the end of class last time is that there's a trade-off between instructions per program and cycles per instruction. So generally what happens, if you try to minimize one, you maximize it makes the other one bigger. So the question is it really, is it really worthwhile to do, if you make one small and you make the other one bigger, is it really worth it? What is the exact trade-off? And so it's interesting because in the history of computing and computer organization, from the very beginning, this, here, remember, this is ISA 3, this is microcode 2, and this is logic gate 1. So, and then there's more up here. And from the very early in the history of electronic computers, this microcode level, Maurice Wilkes was actually the pioneer who did this. It emerged very early in the history of computers, and that's where we get this cycles per instruction, because it takes more than one cycle to implement one instruction. Okay, so the fact that we have cycles per instruction is due to the presence of this level, this MIC2 level. But a very interesting thing happened about 15, 20 years ago. There was, people began to start thinking outside the box, and a new design philosophy emerged called RISC. Now RISC stands for Reduced Instruction Set Computer. And all those early designs that had this MIC2 level were consequently known as CISC, which stands for Complex Instruction Set Computer. And the RISC versus CISC design philosophy is based on the trade-offs between those first 2 terms. So what RISC does, let's go back to the system performance equation in figure 12.33. What the RISC philosophy is they minimize the number of cycles per instruction, even at the expense of having more instructions per program. Whereas the old, and that's in contrast to the old CISC design philosophy, where you want to have few instructions even though they take a lot of cycles, microcode cycles. And in fact what happens is, guess what? What is the ultimate way to minimize this here, in the system performance equation? What's the way to minimize that middle term as much as possible? Cycles per instruction. How many cycles do you think it can be minimized to? You remember when we did fetch, decode, increment? Remember we fetched and we did PC gets PC plus 1, and those took cycles, blah 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 blah, and then we would do the arithmetic shift left or whatever, and it would take a rotate, another shift, and and others took, we had to. So what's the smallest number of cycles per instruction do you think if you took this to the max, to the extreme? 1. Think about this. 1. If there is 1 cycle per instruction, basically what are you saying? You're programming in microcode. Well, there's 2 ways to look at it. What happens is these are collapsed. You can either say there's no ISA 3, there's only MIC2, or you could say there's no MIC2, there's only an ISA 3. I mean, what you call it is. We usually call it ISA 3 still and say that this one's gone. But conceptually, you can think of it either one as being missing. And that, in fact, is what the RISC design philosophy is. Have every instruction execute in one cycle. And they say, and so, but we know, so what's the trade-off? We know what's going to happen if we do that. Our instructions per program, it's going to take what? We're going to have to, in order to write a program, we're going to have to do what? We're going to have to write more instructions. Do you see what I mean? So right off the bat, you guys, what can you say about a program that's written for a RISC machine? Two programs, one written for a CISC machine and one written for a RISC machine. Which one has a bigger object code file size? The RISC. So the programs are going to be bulkier. But you see, in the early days, memory was expensive and small. But nowadays, what? Oh, we can afford it. Are you with me? See, so that's one of the things that happen. So microcode, level MIC2, it's used in CISC machines, but it's absent in RISC machines. And now there are a set number of, did you have a question?
Yeah, it's just a side question. What do machines run on today, RISC or CISC?
That is a really good question. The question is, what machines run today? And there's two great, big, dominant chips in the marketplace today.
Oh, ARM and
All of your Intel chips, all of the Intel chips, the x86 architecture, that from the get-go has been CISC. And I even have, there's a section in this chapter of the book that shows a little bit of the microcode behind the Intel chips. On the other hand, all mobile devices, or not all, but 99.9% of mobile devices use a chip called ARM. And guess what ARM is? ARM is an acronym. ARM is an acronym that has R as an acronym. And this stands for Advanced RISC Machine. So mobile is because they're newer. See, legacy x86 is still predominant because it's legacy. It's difficult to change, rewrite operating systems and applications, and But mobile stuff, that's more recent, and so when they were able to start fresh, and so ARM dominates. There's probably, and because there's more devices, there's probably more ARM chips than there are Intel chips, Intel AMD chips. Because mobile devices far outnumber laptops and desktops and even servers.
Wow, that's neat. So with the whole kind of mobile revolution, they got to start a kind of
start fresh. Yeah.
Really,
yeah, it's very nice. So now there are a certain number of design principles. And the very first one is the numero uno design principle, and all the other principles follow from that. Now think about this, you guys. If every instruction happens in just one cycle, that means that the program counter has to be able to be incremented at the same time in that one cycle. Do you see what we're saying? Okay, so what's the number one principle? Each ISA 3 instruction except for load and store. Now why except for load and store? That load and store does what? Mem read, mem write. And there's no way to eliminate the mem read, mem write delays. But we already saw the way to mitigate that. With what? With cache. So as long as you can get like a 95% cache hit rate, you're not going to stall very much. Are you with me? You can just boom, get them out of the just get it immediately out of the cache. So each ISA 3 instruction, except for load and store, executes in one cycle. Number two, because it's in one cycle, there's no microcode. It's basically like you're programming in microcode. I mean, the ISA 3 is the microcode. All right. Furthermore, now think about this. The third one is every ISA 3 instruction is the same length. Now why does it have to be the same length? Program counter, and you always just get the next instruction and you don't have to say, oh, is it unary, is it not, are there more bytes following, da 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 da. Are you with me? So you can only do that if they're only one, because if they're different lengths, then you got to get part of it and see if there's more than one, and then get fetch. So you get fetch just one. So that means every instruction has to be the same length. Whoa, that's a big deal. And furthermore, what about the addressing modes? There can never. You guys remember how indexed addressing works in PEP 9? We just did indexed addressing. How does indexed addressing work? You have to take what? There's an index register.
And you add that to the operand.
And then the addressing mode adds that to the operand. So now you can't have indexed addressing because it would take more cycles to add the index register to the operand specifier. Do you see what I mean? And that would take an extra cycle. You'd have to add. So what has to happen is that computation has to be written out. The compiler has to do the computations for all those access methods for arrays and pointers and other things like that. Yeah. So you see that makes more instructions have to execute. But on the other hand, those instructions each execute in just what? One cycle. So we take the trade-off. So there are only a few simple addressing modes. And furthermore, all arithmetic and logic operations take place entirely in the CPU. Now let's think about this for a minute. Do you remember how in PEP 9, if we do add accumulator, how does the add accumulator instruction work in PEP 9? It adds what to what? Let's say add accumulator this direct.
So it would add this to the accumulator?
And put the result where?
In the accumulator.
In the accumulator. And it took it from where? What is this? Direct addressing.
So direct from memory?
From memory. You know, if you do from memory, it's always from memory and to the accumulator, and it's put in the accumulator. Well, that's a whole lot of what? That's a whole lot of memory references. Are you with me? So with the RISC design, that's called an accumulator machine. CoSc machines are sometimes called accumulator machines because, you know, lots of references to memory. But now with the RISC machine, all the operations are done between two registers in the CPU. So load and store are the exceptional ones, that are the only ones that actually have to go to main memory across that bus, across the system bus. So when you add two things in a RISC machine, what do? You add the content of one register to the content of a second register, and you put the result in a third register. So those are called, and so load store is the only thing that accesses memory. Yeah. That's a good question. Before that, you do have to load it, and afterwards you do have to store it. But here's what happens. The memory bank in a RISC machine is like a small cache. And the compiler, what the compiler does is the compiler assigns the variables that it's working with to registers. And so you load it once, you load the other one once, and then you can do all those arithmetic operations in a loop maybe, and they can all be in the CPU. There's a big register bank that acts like a small cache. And it only needs to be stored it only stores it when it needs it.
Okay.
Do you see what I mean? So it's like it treats the register bank like a cache. Right, if they're random accesses to memory, right. But still you have but on the other hand, the cache is an integral part of this anyway, so even though the register bank is its own cache, I mean the L1 cache is also there that can get things in one cycle. The L1 cache, remember the L1 is...
CoSc machine?
Well, CoSc machines also have caches. In fact, the CoSc proponent, there's kind of a little bit of a resurgence now of CoSc people who are trying to make a comeback. It's kind of interesting because they're saying, oh yeah, the LLVM thing, we can tune this to this, and they're trying to think outside the RISC box now and going back to CoSc. It's kind of interesting. It's really fascinating design trends. All right. And the data sections are designed for deep pipelining, but also CISC machines also can have deep pipelining, but the argument for RISC is that RISCs are especially effective at pipelining, at deep pipelining. That's that third factor in the system performance equation. All right, and then here's some information. I don't want to dwell on this. There's some AMD microcode. It's for the MOVE-SB instruction in the x86 architecture. You can check that out on your own. Now here's another interesting thing that we're going to do is we're going to learn a new, as an example of a RISC machine, we're going to learn a new chip. Well, it's not new to us. And it's called the MIPS chip. MIPS stands for Microprocessor Without Interlocked Pipeline Stages. And let me tell you guys, if you guys ever go to grad school or anything, this is a classic design that is well known in the computer science education community. All right, MIPS. It was designed at Stanford and UC Berkeley, and it was used in the Nintendo game consoles. So it's a commercial chip. And MIPS and ARM are the most common RISC processors. ARM, we mentioned that just a minute ago. Now, and here actually there's an interesting development with this MIPS chip. You guys are familiar with the software open source concept, where you don't have to pay to buy a program if it's open source, and everybody can see the code and you can use it freely. Well, there's a new development, hardware open source. And so the people at Stanford and Berkeley have actually set up a consortium. So even though there's a commercial version of MIPS, there is a new, you can look this up on, you can Google this. There's a new effort to make this architecture an open source chip. So you don't have to pay anybody to, fabricate it up and use it. So we'll see if open source hardware will take off, but this is kind of a new development that's kind of exciting. So if it does, this is the architecture that we might see more of in open source hardware. Yeah, you can fab, little, small projects or just whatever open source, same thing as open source software. Everybody you can see it, you know what the architecture is, you know what the specs are, you can use it, you can build your own little system with it. Yeah, for hardware devices, So it has an interesting history, and it also might have an interesting future. We don't know yet. This is all brand new. So here in figure 12.35, so now what we're going to do is we're going to learn the MIPS. What we'll do now is we're going to learn the MIPS ISA 3 level. Okay? So these are the registers in figure 12.35. And you can see there's actually two versions of the MIPS machine. There's a 32-bit version and a 64-bit version. And we're going to look at the 32-bit version. And so each one of those registers is 32 bits wide. And how many of them are there? How many registers are there in part A? There's 32. Addressed from what to what? 0 to 31. So that's the register bank. And by the way, you guys, this register bank looks just like the PEP9 CPU register bank. It's a 2-port output and a 1-port input. There's an A and a B bus and a C going out and a C bus going in, and that's the registers in the register bank. Okay? And there's one constant register, that's the 0 register, which is at register address 0. And okay, so now, because there are 32 registers in the register bank, how many bits does it take to specify which register? 2 to the what is 32. So does everybody see then? It takes 5 bits. So remember when we had an A and a B going into the register bank? Well, there's 5 lines for the MIPS A and the B. And register 0 is a 0 constant. And we can take a look at some of these. Look at register number 28, that's $. The MIPS notation is to prefix the register with a $. So you can tell, like, for example, later on in an example, if we ever use like $T2, its address is what? 10. And $A3, that address is 7. And what do you suppose this address 29, what is that one? $SP, what does that sound like? That's the stack pointer. All right, so that's SP. Are you with me? And $GP, that's the global pointer. Where are globals stored in the C memory model? At a fixed location in memory. So G is the pointer to that fixed location in memory of where the globals are. And those others have other various meanings. FP is called the frame pointer. RA is the return address. And there are others. I don't think I want to take the time to describe each one. But look, in comparison, for part B, this is a scale drawing. Because these are 32 bits wide, but and how big are the PEP9 registers? 16. So they're half, and there's fewer of them. But on the other hand, MIPS is what? Reduced instruction set, and PEP9 is what? Complex instruction set. So even though it's small, it's still complex because it has all these complicated addressing modes. And it has a microcode. It has microcode. Are you with me? But that's just a little scale drawing comparison. So in the MIPS instruction set, all instructions are exactly 32 bits long. Okay? All instructions have to have the same length. All binary operations are between two source registers. In the MIPS terminology, it's RS and RT. And the result is placed in a destination register, which is known as RD. And the only instructions that access main memory are the load and store instructions. And all instructions except load and store take one cycle. So that's the numero uno RISC design philosophy. You'll be amazed. It'll be, I mean, we're used to doing all this microcode. You'll see. We'll do. You know, when we list the microcode, we're gonna take a look at some MIPS microcode. You know how we used to have 1, 2, 3, 4, 5. Every MIPS instruction has what? 1, and then boom, 1 cycle. Include that it's going to include incrementing the program counter. Oh, by the way, you guys, what is missing from this in Figure 12.35? What register is missing here? There's a $SP for the stack pointer. There's not a $sign what? PC. The program counter is not one of these in here. The program counter has to be outside the register bank with specialized circuitry to increment the program counter so that it can happen at the same time the program is executing, the instruction is executing. Do you see what I mean? So that's one aspect of the organization of a RISC machine. And memory is still byte addressable, so in Figure 12.36 we have the MIPS von Neumann cycle. We fetch the instruction at the address in the program counter. Simultaneously, what happens?
Add to the program.
And how much?
4.
Why always 4?
I guess that's the size of the instruction.
Of the instruction. 4 bytes is 32 bits.
Oh yeah.
Do you see why that is? Mm-hmm. So it's always 4. I mean, if you're going to do the next instruction, it's always 4 more than the previous. So you're going to have a specialized adder that adds 4 on the fly that's outside the ALU. You see what we're saying? Okay. Decode the instruction specifier and execute the instruction fetched. All that happens in one cycle. Now, the ISA 3 level is a little involved. All right. So let me just state at the outset that there are 6 addressing modes. All right? And each one of these addressing modes can execute in one cycle. I mean, so there are 6 of them. They are known as immediate. Now, we've done immediate addressing, right? Immediate addressing, where's the operand? In the operand, especially, yes, it's in the instruction itself. Mm-hmm. Right, so that's the same idea, okay? So immediate. Register, we already talked about register. That's where you take one register plus another register, put the result in the third register, right? So there's register, immediate addressing, register addressing, base with load, base with store. So there's the load and the store. And then another one is PC relative. Now the PC relative instructions are how you do branches. So think about it for a minute. And this, by the way, is very common. Unfortunately, we don't have it in PEP 8 to illustrate how it works. But it's very common and we should know what it is. Think about it for a minute. Suppose you want to branch, suppose you're doing an if statement and you want to say branch to the else. So branch, boom, we're going to branch to the else, right? Well, look, suppose your program is in memory somewhere and you want to branch to else. And so you say, oh, I need to know what the address of what I'm going to branch to, so branch to else. But now suppose that program is not there in memory. Suppose the operating system took it out when it was interrupted and then put it back in a different place in memory. And now how are you going to do branch to else? Do you see what I'm saying? Because now the program has been reloaded to another spot in memory. So now how are you going to do that branch to else? Well, the solution is what? PC relative. Because if the program has been moved over here, well, the program counter now is here, and relative to the program counter, you would branch to the same place relative to the program counter. So that helps executing branch instructions when the program is relocated to different areas of memory. Is everybody, are you with me on this? It's like stack relative, but it's PC relative, and it's good for branching instructions. And then we have an addressing mode called pseudo-direct, which is for doing unconditional branches to really far away. But it's not quite direct, it's pseudo-direct. And then, with these 6 addressing modes, there are 3 different instruction types. There's I-type, R-type, and J-type. And then, with these 6 addressing modes and these 3 instructions, there are 5 instruction formats. So it's all kind of complicated. You got 6 of one, 3 of one, and 5 different instruction formats of the other. So I don't want to spend an inordinate amount of time going through how these are all interrelated, but it's all laid out in this chapter, in these following figures. So let's take a look at them briefly. Figure 12.37. How many addressing modes did we say? 6. So here they all are. We have immediate, register, base with load, base with store, PC relative, and pseudo-direct. And how many different types did we say? 3. So notice that immediate is an I-type instruction, register is an R-type instruction, base with load is an I-type instruction, base with store is an I-type instruction, PC relative is an I-type instruction, and pseudo-direct is a J-type instruction. So that's just how those things match up. And now for the operands, there is, in general, there is one destination and 1 or 2 sources for each. Now, let's just run through this real quick and take a look at some of this notation. Oh, by the way, the notation here that I use to describe this is not the standard MIPS notation. The notation that I use here is made to be similar to the way we notate PEP 9. And the biggest difference is that PEP 9 numbers the bits like an array in C. Sub 0 is the first one, sub 1, sub 2, sub 3, sub 4. Now, it's very common in industry to do it the other way around. So sub 0 is the least significant, and sub 1, and it goes to the left. And sub 1 is the next more significant, and sub 2, so it goes the other way around. But so be aware, if you're looking up in the MIPS documentation, that this is different. So let's take a look at the first. Immediate addressing, I-type instruction, and now the SE under source, SE, that stands for sign extension. Because look, the immediate field cannot be a full 32-bit value. Why not? Why can't the immediate field of an instruction be full 32 bits? Because you got to have room for the opcode. Do you see what we're saying? But all the instructions have to be the same length. So that means that means we can't store a 32-bit value in the immediate field. So we can only store up to something less than 2 to the 32. So the IM is the immediate field of the instruction. So that's the meaning of SE. And then the register is the R type, And this REG, that stands for registers. Now, let's take a look at the R type. The destination is register sub RD. Now, what do you suppose the RD field is? How many bits do you suppose are in the RD field? Based on what we just observed a few minutes ago. 5, because it's going to access one of the 32 registers, and it takes 5 bits. And then base with load, we have this sign extension of the immediate field, and then plus the register RB, and then mem of that. So load goes from memory to a register. Do you see how that works? So here's from this memory location to this register, and base with store goes from this register to main memory. So that's the load and the store. And then the PC relative. So the PC relative, the source is, the details of that are all described in the chapter. Now, figure 12.38. Now, how many? We said there are 5 instruction formats. So here are the 5 instruction formats. So here we have, in figure 12.38, we have part A, B, C, D, E. So these are the 5 instruction formats based. So in part A of figure 12.38 shows the fields for immediate addressing with the I-type instruction. So we see how many bits, you see how many bits are in the immediate field there. Just reading off the figures, 16. And then the destination field is 5, the source register field is 5 bits, and the opcode is 6 bits. All the opcodes are 6 bits. What's 2 to the 6? See, but there's more than 64 instructions in the MIPS instruction set. So how can that be if the opcode field is only 6 bits? Well, some of the instructions have this function field, which is the last 6 bits of the register addressing with the R-type instruction. And so what can happen is it's the opcode plus the function field determines what the operation is. Do you see how that works? So this is kind of like this function field is kind of like an extended opcode to let us have more instructions in the instruction set. So B is register addressing with the R-type instruction. C is base addressing with the I-type instruction, and each one of these fields is it shows where the binary is for each one of these fields. It's all laid out like that. And then the PC relative addressing with the I-type instruction is in part D of the figure. And then part E shows the pseudo direct addressing with the J-type instruction. So these tables, well, you know, this addressing mode table in figure 12.37, this instruction formats in figure 12.38, all this will be available to you on the exam. And so what we need to be able to do is we need to be able to translate. This next figure 12.39, shows a few of the instructions in the instruction set at the ISA 3 level. And the slide just before this describes what each one of those instruction fields is. So you know how in PEP 9 we have the addressing AAA field? Well, here we have the MIPS SSSSS field and the MIPS TTTTT field. Okay, so if you look here at the instruction set, you see here add, what's the opcode for add? Can you tell by this first line on figure 12.39? What's the opcode for add? Which bits were in the opcode? First 6 bits. So here, if we go here, so what's the opcode for add? 000000. What's the opcode for add immediate? 001000. What's the opcode for subtract? Hey, how can that be 000000? I thought that was the opcode for add. Ah, it has a different function field. See? Are you with me? Does everybody see how that worked? So these letters like DDD and III and HHH. Oh, HHH? What is that? HHH is the what? HHHHH. That's a what? So check out the shift amount. HHHHH. Where's the shift amount used? Let's find an H. You see here, down here, it's SLL stands for what? Shift left logical. And what does this HHHHH field say? How much to shift? In PEP 9, you can only do shift 1 bit, but you can say shift 2 bits, shift 3 bits, shift 4 bits, shift 5 bits, shift, 20 bits in one cycle. In one cycle. So the hardware does that probably with what's called a barrel shifter. Are you with me? So you don't have to loop through.
You can multiply way more efficiently.
You can, oh yeah, you can multiply really efficiently. Yeah. Although you can multiply in software, although it's frequently done in hardware integer units. But anyway. But for encryption or something, you have an encryption algorithm and you need to shift more than once. You can do it all in. So that's the H field. So we have destination registers, base registers, shift amounts. Immediate values are sign extended for addition and 0 extended for and or. And then AAA fields are address offset fields. So again, here, I don't want to go through every single one of these. And then, and also notice that there is that the mnemonic for load and store. LB is load byte, LW is load word. Now a word in MIPS is not 2 bytes, it's what? How big of a computer is this?
32, I think
it's a 32-bit, remember we said there are actually 2 versions, there's a 64-bit version and a 32, we're studying the 32-bit version.
So this would be 32.
So a word is 4 bytes in MIPS. All right? So LB is load byte, LW is load word. LUI is load upper immediate. We'll do an example of that in a minute. SB is store byte, SW is store word. And then here's the branch. Look, it's the same mnemonics, kind of. No, I take it back. They're not the same mnemonics. BEQ is branch if equal to. BGEZ is branch if greater than or equal to 0. Now here's what's interesting about MIPS with these branch instructions. There are no status bits. Instead, all branches compare the contents of 2 registers and branches accordingly. So there's no NZVC bits. Intel x86, they have NZVC bits. Most processors do, but the MIPS does not. So how do you know if there's ever an overflow? Well, there's 2 versions of add. Okay, so there's an add instruction and then there is an add unsigned instruction. And what happens is add, if there is an overflow, it causes a trap and the operating system takes over. But if you don't want the trap to happen, if you don't want to check the NZVC bit, or there are no NZVC bits, but if you want the addition to happen without checking for overflow, you do add unsigned. So there's 2 different instructions, one of which will trap if you get an overflow. A lot of people say, I've seen discussions on Google, on the internet. Where are the status bits in MIPS? MIPS doesn't have status bits. Interesting. got to kind of get your head around that. So yeah. So anyway, next time what we'll do is we'll take a look at some examples, at some example code, and I recommend that you go ahead and read the material in the chapter. If you read through that and start working on the homework, I think that'll help us with our examples that we do on Thursday. And now also, you guys, we have our last lab on Friday. So, good deal. See you in a few days.